All right. Hi, guys. Today I'm going to talk about the non-fossil fuel thermal power generation. So that just means getting um, getting electricity from non-fossil fuels, right? So not coal and natural gas, but still using thermal energy to do that. So basically, still releasing heat and then changing that into electrical energy. So that means that we're going to be looking at nuclear, geothermal, and biomass as our different energy sources that we're looking at. We're going to start out by first looking at nuclear energy. So, nuclear energy is, just to make sure we are clear about this, not chemical energy, right? So, chemical energy would be when you take certain molecules and combine them, but then you still have those atoms left. So, right, more, you know, for example, we've been talking about taking carbon and oxygen and combining that into CO2 with fossil fuels, right? So that's a chemical reaction. You still have this carbon, you still have the oxygen, you're just changing it into CO2 versus nuclear energy where you're taking, like, for example, hydrogen and hydrogen. It's more complicated than this, and turn it into helium. Um, right? You no longer have your hydrogens, instead you have a helium. So that's kind of a simplified view of that, but that's how nuclear energy is different than chemical energy. So So quick, a little warm up here. So if you would pause the video, read through these questions, and then you can press play in just a second and listen to me talk about them. So go ahead and press pause now, please. Okay, welcome back. Uh, First one is, what is the number in the top of every box in the periodic table? That would be referring to the six right here. That's called the atomic number, or and it basically refers to, and it comes from, right, the number of protons. So, right, so if you had in the example of carbon, carbon has six protons, so that's what the six means. Helium, which is two, has two protons. So that's what distinguishes one element from another element. So number three, what does E equals mc squared mean? E equals mc squared is an equation that turns energy, relates energy and mass. Um, so basically, if you were to take right, a certain amount of mass and you just kind of annihilate it, get rid of it, you would multiply that by c squared, which is the speed of light squared, which isn't super important other than it's a really big number, right? The speed of light is 3 times 10 to the 8. Oops. 8. So then you take that number and you square it. So basically, what this is telling you is that if you annihilate a very small amount of mass, if you get rid of a very small amount of mass, you're going to end up with a lot of energy being released. And that is important because in nuclear reactions, you end up with less mass than you started. So it's an equation that tells us about nuclear reactions, basically. Number four, protons are positive charges. You may already know, like charges repel, similar to magnets. Like helium, for example, has two protons right next to each other um, in the nucleus, right? So it's got two protons right there. And if you don't know this, right, that in general, like a proton does not want to be next to another proton because they're both positive charged. Just like magnets, like the north side of a magnet doesn't like to be next to the other part of the magnet. Yet when you put them together in the nucleus, they're totally fine hanging out next to each other. And this is because if you can get these two, this is called the force of a repulsion, that would be called the electrostatic or electromagnetic force, or electrostatic force. Um, And if you can get them close enough to each other, something called the strong force, which is a force of attraction, um, take over. And so holding those two things, those two protons together. So basically, The strong force doesn't work if it's too far away. So if I separate those two positive charges a little bit, then right the strong force becomes not strong, and the electromagnetic force takes over, which is a force of repulsion. However, I can get them closer and closer and closer. At some point, the strong force takes over and is much stronger than the electromagnetic force, but it doesn't work if you get very far away. So that's what's going on there. So there's two types of nuclear reactions. There's something called fission. Oops, here. Something called fission. So fission is what we use in power plants. And basically, you're taking a large atom and you're tearing it into multiple pieces, basically. So most commonly, we're taking PM-235. That's this right here. The 235 refers to its atomic mass, and splitting it into two different atoms. And you get a lot of energy when that happens. So, for example, I mean, here's the reaction for that. And the only thing that I really want to note out of this reaction is that you start out with uranium and a neutron, and you end up with, right, note that there's no more uranium left. So that's again noting the difference between a nuclear reaction and a chemical reaction, that you start with a uranium atom and you don't have an uranium atom at the end, versus a chemical reaction where you still have all the atoms you started with. So, fission can take place at low temps. So heat is not required to make this happen. And so just kind of noting that. And when I say low temperatures, uh, it's not necessarily referring to like wintertime or something like that, but it's going to be in contrast to fusion, which I'm going to talk about. Well, we'll talk about it right now. So fusion is the other one. So fusion happens in the sun. We can't do fusion on Earth because it requires high temperatures. And so when I say high temperatures, like thousands of degrees, basically, it has to be really hot. The reason is that basically when you combine these atoms, you need to, they're collisions. So we're basically taking, in this case, this tritium and this deuterium, and you're crashing it together to and making them stick together. And so you may remember from chemistry that like basically atoms vibrate back and forth, right? So the hotter you get them, the more they vibrate and move, right? So basically, the hotter things are, the faster they're moving, and so the faster they're moving, the more likely they are to collide and stick together. So at lower temps, like temperatures we have on Earth, they just aren't moving fast enough to collide and stick together. But if you get them hot enough, then they're moving fast enough that when they collide, they stick together. So that's why it's required for it to be such hot. In this case, you can see we're taking these hydrogen atoms. They're called hydrogen, right? Even though they aren't your typical hydrogen atom, right? Deuterium and tritium. The reason that it is this is because, right? Note the one proton and the one proton making it hydrogen. They're just different isotopes of hydrogen. Uh, Note that we combine these and we get a helium atom out, we get a neutron out, and we get a bunch of energy out. So, um, there we go. Next up, so where does the energy come from? So going back to the warm up where we talked about the E equals mc squared. So when we have this energy released, how does that energy come out? And remember, E equals mc squared is basically if you take mass and turn it into energy, meaning if you annihilate some mass. So let's take a look at this. So let's start with our fission here. I'll start with this first one. And if we look at this, these numbers are the atomic masses. Right, two neutrons would be uh, basically two atomic masses. Um, so remember that these would be them in what's called AMUs, which is atomic mass unit, and it just basically refers to like one proton uh, has an atomic mass unit of one. So it's basically the amount of things in the nucleus, because a proton and a neutron are more or less the same mass. So when we talk about an AMU, that's atomic mass unit, and it refers to the number of things in the nucleus because both protons and neutrons have approximately the same mass. So it's a unit of mass, a very small unit of mass. So, um, so let's see here. So this would be, right, if we were to look at the atomic mass unit for this, Right, we start out with one neutron and then 235 protons and neutrons. So we start out with, we're keeping track of the mass at the beginning. We start out with basically 1 plus 235. Again, doing this in terms of atomic mass units. This is fission. At the end, so I want to find the difference. I want to see how much I lost, right? So at the end, 2 minus, well, I have a slightly different word here. Let me see here, sorry. We have 143 plus 90 plus 2. Interesting. So let's take a look. We'll just keep going here. Plus 235. So then we got 1. Back real quick, just make sure I didn't mess this up. No, we're still good. Okay. So minus 143 minus 90 minus 2. The reason, again, I'm trying to do this is this is basically the amount of mass I start with minus the amount of mass that I end with, right? And if we do that, we're basically going to have, right, 236 minus 143 minus 90 minus 2. So that is a difference of 1 atomic mass unit. So, right, meaning that when you do this reaction, you've basically lost the equivalent of 1 proton or 1 neutron in mass, right? You have less mass than when you started, right? Because you start out with 236, you end with 235, and so therefore you've lost 1 atomic mass unit. Okay, now the problem is I can't just take my 1 and plug it into E equals mc squared. The m needs to be in kilograms. So what we got to do next is change this into kilograms. So to change it into kilograms, I'm just going to do the 1 atomic mass unit times by 1.66 times by 10 to the negative 27 kilograms. And that's obviously going to be just equal to 1.66 times by 10 to the negative 7 kilograms. And so that's how much mass we've lost. So we can plug that into the E equals mc squared thing. And that's just going to be 1.66 times by 10 to the negative 27 and times by 3 times by 10 to the 8 squared. And you will get that. This 1.66 times by 27 times by 3 10 to the 8. And so that means that we have just released 1.49 times by 10 to the negative 10 joules. Okay, so that doesn't sound like very much energy, but keep in mind that this is the amount of energy released from one atom, right, doing this. And this might be an oversimplified view, right? This might be, a little bit inaccurate, but we're trying to get the idea here of how much energy is being released. So, but keep in mind, like, even though that's not very much, it's from one atom of energy. So let's take a look at the next, right, fusion. And we're just going to take a look at the amount that we start out with. Keep in mind, 1 neutron has an atomic mass of 1. So this is going to give us, right, the amount that we start out with, which is going to be, right, we start with 6. We start with that much mass, right? At the end, we have By the way, Q is the amount of energy released. That's what this Q is about. So if you were wondering. And so basically the mass we start with minus the mass we end with. And so we're going to end up with 0.0274 AMUs. Right, so that's the difference. That's how much energy or mass we've lost. Same process, we got to change this into kilograms. All right, here we are back. Sorry about that. Just got a little bit messed up. So anyway, we have 0.0274 AMU. So now we got to change that into the amount of energy that we, or into kilograms. So first up, take our mass here. 0. See, I gotta go back. 0.0274 AMUs. Each one of those AMUs is 1.66 by 10 to the negative 27 kilograms. And so that's going to get us, let's see here, 4.55 times by 10 to the negative 29 kilograms. Okay, so now we can take that, plug that into the E equals mc squared equation to see how much energy that ends up being. So, right, take that mass, the 4.55, 10 to the negative 29, multiply that by the speed of light squared, and we're going to get 4.09 times by 10 to the negative 12 joules. Okay, so a couple things to note, right? Again, a really small amount of energy, but keep in mind this is basically from one nuclear reaction. So you'll also note that it's less than fission. In general, fusion releases more energy than fission does, and part of it, right, is based on the mass, right? So I mean, you look at how much mass we started with here, which is roughly 5 atomic mass units versus um, the fission, right, which started with like 235. So even though it's, from a mass standpoint, fusion is releasing a lot more energy than fission is, but even though that's not reflected in the numbers here, and that's because um, basically fusion, right, every time you fuse something, there's a bigger change in mass than when you do fission. So unfortunately, at this moment, we're not able to do fusion on Earth. But if we did, there's a couple really big benefits. So first up, like, right, it just doesn't take that much mass in order to get a relatively similar amount of energy. The second thing is, right, some of these things that are left over, well, the things that start and the things that are left over are radioactive, right? So every time you're doing fission materials dealing with radioactive materials, and so as a result, right, then we'll get into this, you have to store it, and there's issues related to that. The other thing is we have a lot of hydrogen, so like if we could figure out fusion, we would suddenly have, like, there would be a lot of we have almost tons of hydrogen that we could use to do this. So anyway, um, that's kind of our little thing. So I'm not going to ask you to do this math, but it is giving you an idea of showing you how nuclear reactions work, and also like what this E equals mc squared equation is, because it's one of those equations that you probably know or have heard of before, but you don't actually know what it does. This is what it does. It shows you how much energy is released during a nuclear reaction. So we can use that equation on this one too. The sun generates energy at a rate of 3.9 times 10 to the negative 26 watts, or not negative 10 to the 26. Use this value to confirm the sun loses mass at about 4 million tons per second. So real quick, so all we got to do is use our E squared. We know, right, watts would be in joules per second. So we can just use this number for our energy because because it wants the 4 million tons per second, we can just use the 3.9 times 10 to the 26 joules uh, as joules instead of watts. So we'll just put that in here. So you got 3.9 times by 10 to the 26 joules in for your energy. We are looking for M, and you got 3 times 10 to the 8 squared on that side of the equation. So 3.9 e to the 26 um, divided by, right, just going to move, divided by 3 times 10 to the 8 squared gives you, right, your M is equal to 4.33 times by 10 to the 9 kilograms, right? So now we just got to change kilograms into tons. So what did I just say here? 4.33 times by 10 to the 9. So go to Google, just say convert 4.33 kilograms to tons. That. And it says 4.77, 4,773,000 tons. So almost 5 million tons. So, so there you go. If you go back to, right, if we go back to the original question, it just said convert, show that it's equal to about 4 million tons per second. So that means that basically the sun is losing 4.33 times 10 to the 9 kilograms, and then right, we just convert our kilograms into tons, and there you go. Real quick, so the reason that this is happening is basically the amount of energy that is required to keep that atom together. So we call that the binding energy. Um, and so we know that it is very steep as you put together an atom. So it's the amount of energy required to assemble an atom. So like basically to go from hydrogen to helium is a big difference in energy. It takes a lot of energy to assemble or also disassemble an atom. So, oh, sorry, binding energy is the amount of energy it takes to tear an atom apart. So to go from um, to take helium and then now tear it apart into all of its pieces. So if you assemble the atom, you get that energy out, right? Um, so we see that going from hydrogen to helium, that's going to release a lot of energy as you build this up. That's going to right, you're going to release a lot of energy. It would take that much energy to tear the hydrogen into pieces and get it to be small again. So we see that you can keep getting energy released as you go from hydrogen and then build into carbon, lithium, oxygen, so on and so forth. But do note that it goes ahead and peaks here at iron. So as you build things all the way up to iron, you will continually get things released. Obviously, like for our standpoint in nuclear reactions, and for things like the sun, they're mostly concerned with going from hydrogen into helium. On Earth, right, we're starting down here with plutonium and uranium, and we're going this way. So you can see that not as much energy is released as you tear that energy as that that atom into pieces. So the reason that that's notable is that, right, because we're tearing it into pieces, we're moving to the left on this, and therefore still moving up the graph, and so still releasing energy. If you go down the graph, it takes energy. So if we were to try to make anything big, like take, let's say, iron and try to build it into something else like gold, then I don't think Ge is actually gold, but right, to move it up, Au, I think that's gold. If you're going to move it up the thing, that would actually take energy. So for just for fun, stars are taking hydrogen and turning them into helium primarily. Um, and stars will actually fuse things all the way up to iron, and then they'll stop because if they fuse things beyond iron, then it takes energy away from the star, cooling the star off. So they're not going to do that. So anyway, but we do fission because we can. We can't do fusion on Earth. So just a brief introduction to like how, not a lot, but how a nuclear reactor works. You have the fuel elements here um, in your um, in your kind of boiler area, right? So you got this, it's all encased in water here, and you got this it's usually uranium 235. These and so they are reacting, right? So they're undergoing nuclear reactions, and so then they're therefore releasing energy that the water is absorbing, and then we're using that water, um, right? Following it along, we're using that water to power a little, to power our turbine, which is then right is this is steam generator, basically, a a a steam engine more or less, right? So we're using this water heated by the nuclear reactions going on here to power our steam generator. Um, Briefly, we go back and we look at the equation. Note that fission starts with this one neutron. So you got to have this one neutron that triggers this reaction. So you got to have one neutron that kind of comes in. Go back a little bit further, right? One neutron that comes in here that triggers this whole thing to happen. So a neutron collides with uranium 235 and thus breaks this whole thing into pieces. So you gotta, if we go now back to where we are, um, you got to have neutrons that are keeping those nuclear reactions going. So a neutron would maybe collide with uranium atom in here and make that thing go. So to control this whole process, we have these control rods, which are basically lowered into our thing here, and they absorb neutrons. So let's say it gets too hot, too many nuclear reactions, we'll lower the control rods in. The control rods absorb those neutrons that are bouncing around in there. So therefore, that slows the nuclear reaction and cools the whole thing down again. Maybe it's too cold. It's not heating the water enough. You lift the control rods back up again, and right, that releases more neutrons are now able to fly around in there, colliding, creating more nuclear reactions, and therefore continuing going on. So these control rods are just things that absorb neutrons, and so you lower them in, absorbs the neutrons, slows the reaction. Lift them out, neutrons now can collide with the nuclear reaction with uranium, creating heat and nuclear reactions. So that's kind of how that works. Um, so looking at from kind of right stepping back, looking at it as a way of generating electricity, what are the pros and cons on this nuclear reaction? First up, pros, right? So it doesn't emit any carbon pollution. That's a big thing because right, the kind of the theme of this whole lecture series has been on emitting right climate change and carbon in the atmosphere and how that's a problem. So nuclear is really good in that it doesn't emit carbon into the atmosphere. It's also good because we can produce a large amount of constant power, right? So we'll get into this a little bit more when we talk about wind and solar and things like that. But like, right, nuclear power will work, during the day, during the night, whether it's windy, whether it's not windy, whether it's sunny, whether it's not sunny, right? It will always be producing power and not emit any carbon in the atmosphere. And that's really good. It's something called baseline power. So it's producing electricity to meet our general consumption needs, right? Does maybe not the peaks, but it's there for when we need it all the time. So, right, and you can't start these things up and turn them back down very easily. So they basically just run constantly all the time producing electricity. Has a high energy density, right? So meaning that it doesn't actually require that much material to run a nuclear generator. So an example would be that, like for a fairly large size power plant would create enough nuclear waste that would maybe fit under your dining room table. Like it's just not volume wise, it's just not that much space and energy or space. So versus right, we did the calculation last week about the number of coal trains. Oh, your last homework was the amount of coal trains, right? It was something like what, 10 coal trains per week to run a nuclear or a coal power plant. Um, so per week that power plant is using 10 trains worth of coal. In 1 year, this nuclear reactor would use enough, right? Enough waste to then fit under that could basically fit under your dining room table. So just a very small, 1 meter squared type of space. Um, and of course, it has some big cons. We haven't really built that many new nuclear reactors for a really long time. Right, some downsides. It needs to be mined and needs to be enriched. Right, so when we go and mine uranium, generally, we're not just able to find that much uranium 235. We find a lot of uranium 238, and so we have to enrich it to 235, and that takes energy and a lot of mining. So that's obviously anytime we're doing mining that's not so great. You're bad for the environment. You're having to run dump trucks and excavators and all that kind of stuff. Plus, it's just really hard on the environment to be tearing up that big of a chunk of land. Um, Also, always you're disrupting that area and you're messing around with nuclear radioactive material. Once we're done, nuclear waste needs to be stored for hundreds of thousands of years, right? So that's probably the biggest problem that we have right now is what to do with the waste. So, sure, it's only a 1 meter squared worth of waste, but where are you gonna put that, right? It's gonna be radioactive for, you know, arguably thousands, millions of years, and we gotta take care of it. Where do you put it? And there's lots of different ideas on where you can put it. Sometimes it's buried in the ground. Sometimes it's build these kind of little bunkers for them. But either way, that's something that has to be maintained over years and is very expensive to figure out where to put it. And of course, no one wants it, right? No one wants it in their backyard. No one, you don't want a bunch of nuclear radiation hanging around. So, um, that's obviously a problem. And then lastly, radiation risks. So, something could go wrong, and then that's going to release nuclear radiation. And you might remember the Fukushima Daiichi plant from about 10 years ago, the um, the earthquake in Japan where that thing got um, damaged and released nuclear radiation. You probably all heard about oh shoot, what was it called? Why am I not the Russian one or the was the Russian? Anyway, I'll think of it. I can't remember at the moment. Anyway, so obviously there's Three Mile Island, 10 Mile Island in New York, in which something has gone wrong and release that energy into the environment or that radiation into the environment, and that's obviously a concern as well. So there's those things that we need to always be worried about. There's also always a risk of this nuclear waste or nuclear enriched nuclear material being used for things that it shouldn't be. So someone stealing it and using it for harm. Maybe it's making a bomb, or maybe it's just taking it and putting it somewhere that would be bad. So those are obviously things that are not so great the about nuclear radiation. So all right, okay. So looking at our nuclear future, we haven't really been building nuclear power plants in the U.S. There's lots of laws and regulations around it. Um, and so like the average power plant um, in the US, it was built, it's 38.5 billion or years old. Anyway, meaning that they were built in the 60s, the 70s, or the 80s. And so they're generally based on older technology. Think about how far we've come in technology um, since the 60s, 70s, 80s. And of course, they've been updated for sure, but they're just, they're older designs. We've learned a lot since then. And so there are safer, more efficient designs that are being engineered right now. I believe the Bill and Melinda Gates Foundation has been kind of pushing on that to try to come up with better ways to do that, that maybe uses more of the, can utilize more of the nuclear waste so that it's even less nuclear reactive when you're done with it. Um, and so, but anyway, but of course, there's so many regulations that they can't test it. Anymore, uh, or they can't test it in the US very easily. They had plans to test it in China, but that fell through when we had a leadership change in the US, and so then they can test it in China anymore. So, um, but there is a nuclear future that might look different than what we have right now. It's hard to say because we haven't had a chance to go down that road yet. But right, nuclear gets a pretty bad rap because of some of the catastrophes that have happened, and so realizing that there might be some better ways that we could do this, but that hasn't necessarily come to fruition yet. So our next thermal non-fossil fuel plant is geothermal. So that's going to be harnessing thermal energy from inside the earth to produce electricity. So keep in mind that, right, what you need to create electricity using heat is a heat differential. So going from hot to cold, because energy wants to go from hot to cold. So we've right, go. Just a reminder about a heat engine is a heat engine is going to take energy, right? Hot, that heat wants to go from hot to cold, and then we create electricity from that, right? Um, there's a, and so what we need to do in order to create a temperature differential, we drill down into the earth, get something that's hot, and then right we release it out into the cold. So we're using the atmosphere as our cold um, reservoir, and we're using the interior of the earth at a as our hot reservoir. Um, so here's kind of a picture of this. So we're drilling down and into right an area that is much hotter. We're then pumping that heat up, right? Using it to right as a using it to run our steam engine basically, and then we're putting that colder water back down into the earth to be heated back up again. So, just like our fossil fuels, where we're burning them, and our nuclear ones, where just you're trying to get heat, and you're just it's a the where we're getting the heat right is from the interior of the Earth from um, instead of from the from burning something or nuclear reactions. Uh, the biggest problem is that not everywhere can do this, right? Now, I mean, inevitably, you drill down far enough, you're going to get heat, you're going to find heat, right? But it is cost prohibitive, right? Drilling is extremely expensive, and we just can't, you can't just drill forever. We can't do that. We just don't have the capabilities of driving or drilling for kilometers and kilometers, right? So you have to have places where it's generally, you don't have to drill down quite as far in order to get to that heat. So, where is it, right? So you don't want to drill down very far. You got to be someplace that's around volcanoes or hot springs or geysers or plate boundaries. Generally, are going to make it a little bit hotter. So let's take a look at here's a map of the United States. The areas that are hot um, are going to have more energy than the places that are cold. So when you look at this map, we can kind of see that generally speaking, this area right here would be areas that we could use for geothermal energy. We don't have to drill down quite as far in order to really get access to that heat. Versus, basically most of this side of the United States, you can't because right, you could drill down, but there just isn't enough heat. So that in you know geothermal would not be an option for that area simply because there just isn't enough heat down there. Um, so we couldn't do that. So some geothermal's pros and cons, right? It doesn't emit any carbon pollution. So again, just like nuclear, isn't polluting the environment, so that's great. Also, just like nuclear, it can produce large amounts of constant power, right? We again, we have a need for power that is being created, whether it's windy, whether it's not windy, whether it's sunny, whether it's not sunny, whether it's nighttime or daytime, right? Uh, we need ways to just create power constant, and so geothermal plants would do that, right? It's a lot of it can produce a lot of power, and it can do that all the time. It's also relatively cheap to maintain. You're not having to, get trains and trains and trains of coal delivered to you. You're not having to have frack for more um, natural gas. You're not having to mine for more nuclear and enrich more nuclear energy and then try to get rid of it. Once you have this geothermal plant in place, you've made the drilling and done all that. Um, right? It's set to go. You just keep pumping the water out and putting the water back in, and you're not having to keep supplying it, year in and year out or week in or week out, that kind of thing. It just kind of does its thing. So, there's obviously operational costs and things like that, but just in comparison to like let's say a coal plant or a nuclear plant, they're just much cheaper to run because they're not having to be constantly supplied with materials. Um, the cons would be that there are only certain places where you can put you just can't put them in much of the United States, right? And so it's not a good option for everywhere because you just can't put it in a lot of places. They're also expensive to build. If again, you have to drill these really deep wells, and so that's expensive. So it's also something we don't use very much. So every time that we do this, especially in the United States, like it's kind of a new thing. So it's not something that's really caught on. There might be reasons that I don't understand for why we haven't done that, but they're just not as common as building a natural gas plant is much cheaper to build now than a geothermal one. Lastly is biomass. So when we talk about biomass, we're talking about the burning of usually waste products to generate heat to use to make electricity. Many times the companies will have a small biomass generator to supply power for the company, um, and that obviously will be disposing of their waste. So some examples would be sometimes like a paper plant has a certain amount of waste products left over from making paper. And so as a result, they could burn it, incinerate it, use that to then create electricity and to run the paper plant. Um, this also happens with, well, we'll get to there. But basically, it's taking stuff that is in general considered garbage or waste products, burning that to then create electricity. So it generally has the added benefit of getting rid of some garbage and right having the plus side of getting rid of or getting rid of that stuff and then the plus of getting the electricity to use it run it. But these are generally done on smaller scales that are usually to feed the needs of maybe that company. So it's beneficial for the surrounding area because we're not having to run our natural gas plant or our dam or something like that to power that. Right, that energy now can be funneled towards residential. But the downside is it's generally not going out into the grid to power other people's houses. It's just usually not big enough. A fun fact is that actually Seattle, the city of Seattle, has a steam generating plant in downtown Seattle, and they're not creating electricity, but what they are creating is steam that then they run into a lot of the skyscrapers in the downtown region are heated by this steam plant, and it's actually burning biomass stuff to power it stuff, to power it. So um, So types of biomass. So sometimes this might be saw or tree waste or sawdust or tree waste, paper garbage, methane gas from landfills, and dried manure. So right now you can start to see the kind of I was talking about the paper company. I think Georgia Pacific, which I think used to be in Everett. Maybe there's also one in or used to be one in Bellingham, and they were doing that. Let's see here, methane gas from from landfills is actually it's a pretty interesting one. So when you put when you have a landfill, things in the landfill are um, decomposing, and when they decompose, they emit methane. Methane is actually a really terrible greenhouse gas, meaning that it does a lot of damage, and it does like much more damage than CO2 does. It's less common, but when it is into the atmosphere, it does a lot more harm. It's like a stronger greenhouse gas, if you will, than like CO2 or H2O. And so um, methane is considered a pretty big problem. And so what a land when they make landfills and they pile up all the garbage, they'll put pipes in there to collect the methane and they burn it, which is good because it gets rid of the methane, um, which so therefore it's not going out into the environment, and plus you get to you get to make some electricity out of it. So that's extra great. Dried manure, same thing. So a lot of times, like um, dairy farm or something like that, they'll use um, collect the methane out of the manure and basically be able to use that for electricity. So we also have biofuels, so this is slightly different. So it's using, this isn't necessarily talking about it in terms of making electricity, but it is talking about it in terms of decreasing our reliance on fossil fuels. So you probably heard about biodiesel. It's pretty easy to take like a vegetable oil and then turn it into a diesel. That's not a big jump. It doesn't take a lot of processing to do that. And so, sometimes you'll see, you know, diesel trucks and stuff like that driving around with like biodiesel written on the side of it because they're running them on biodiesel. They kind of smell like French fries when they drive by. You maybe heard about ethanol as well. Ethanol is just taking, it's much more, it's like the gas equivalent. And so you're basically, it's made out of corn, I believe. And it basically, you could fill your car with it. Um, does require some modifications to it. Ethanol is actually isn't mixed into fuels. A lot of times when you look at the pump, they might say up to 10% ethanol in there. So you're probably running some ethanol through your car, right now. And then biojet fuel. So it's still being developed. It's not something that's being commonly used versus biodiesel and ethanol are fairly commonly used as of right now. The thing about them is that, right, if we could figure that out, that would be, um, one less thing. So, but right now, airplanes are still, primarily fuel are on fossil fuels, but it would allow us to decrease our fossil fuel usage even more if we were able to figure that out. So, if we're burning things, we maybe think about where is this ultimately coming from. So, right? Where do plants get their mass? From CO2 from the air from the photosynthesis. So just keep in mind that the way that plants work, they work on photosynthesis, which takes in carbon dioxide, CO2. It uses the energy from the sun to break that into carbon and into oxygen, so it breaks it apart. And I guess I should go there. Um, and so basically, that's taking energy from the sun to split these apart. The plant keeps the carbon, which turns it into the plant and releases the CO2 out or the O2 into the back out into the um, atmosphere. So, from a from an energy stand or from a equation standpoint, right, that looks like this. That's taking 6 carbon dioxides, 6 water molecules plus the energy from the sun, and that's turning it into these two things. I don't know what that is called, but that must be the plant matter, and then right releasing the O2 into the atmosphere. So so this is why is this better than carbon, right? We're burning the plant, and so therefore we are releasing carbon into the atmosphere. And so just to kind of remind you that how the carbon cycle works is that you got our plants are pulling this CO2 out of the atmosphere using or using photosynthesis. That is then getting right in the full carbon cycle, it's being right decayed, which is going to release some carbon into the atmosphere. But right, ultimately, if you let it sit there for long enough, meaning millions of years, it's going to turn into fossils and fossil fuels, and then right, of course, which we burn. Um, this kind of right biomass kind of skips this part that takes millions of years, right? That's the part that takes forever, and you just basically burn it and send it back out into the atmosphere. And so we're releasing carbon. Like, yes, we are releasing carbon, but we're releasing carbon that has recently, note the recently in quotations because it might be like in the past 100 years, recently taken out of the atmosphere. So in the a plant maybe over the course of its life has taken that carbon out. We're now just putting it back in. So in theory, this could be considered carbon neutral because right? That plant took that carbon out. We're now just basically releasing it back in to the atmosphere. Um, so whereas with fossil fuels, right, we're taking carbon that's been stored for millions of years and right emitting it into the atmosphere. So that's of course the problem is that we're just adding carbon, more and more carbon to our atmosphere. Versus if we were able to run everything on biofuels, which we can't, there's not enough. Um, we would be simply just putting the same amount of carbon out into the atmosphere that the plants are in. So some pros and cons here. So it is carbon neutral. Again, it is taking carbon that was, just put into the atmosphere, recently put it, or taking carbon that was recently taken out of the atmosphere and just putting it back into the atmosphere. So that's good. It's usually burning some sort of waste product, so it's something that we didn't need. We would probably have to let sit there and decompose anyway. So in that sense, it's getting rid of something we don't need, and so that's good. Some cons are that it still emits carbon into the atmosphere. And so, of course, at a point where we already have way too much carbon in the atmosphere, we do need to try to decrease that. So that's why it's not super great. We generally can only use this on a small scale, right? I mean, the energy content of biomass is just significantly less than that's in coal or natural gas or something like that. And so as a result, like it's very difficult to get enough biomass to be able to actually run a large scale power plant would just be fairly difficult and arguably not that great for the atmosphere. So, um, it works well for or for companies or industries that need the heat, they need the electricity there on site, and they have some sort of product to get rid of, and so that works out well. It works well if you have an incinerator. So some of the I can't remember something like Norway or Sweden or one of those countries. Um, Basically, I mean, they incinerate all their garbage, and they've figured out a way to do it that's really pretty clean, and turn it into electricity. So, is that the best thing for the environment? Perhaps not, but you're getting rid of something that, like if you just leave the garbage sit there, of course, it's going to release methane, and that's not good either. So, there are pluses and minuses to every situation, and anytime you have garbage, that's going to be a problem. So, but meaning like it's not, you can't take biomass and build a huge biomass plant to run, hundreds of thousands of homes. So usually on a smaller scale. So alrighty. So that brings us to the end of this one. I know that was a bit long, but hopefully you found that interesting. And again, let me know if you have any questions. Thanks. Bye.